Hello and welcome into the example video for lesson 16 for Precalculus 2. In this video, we're going to look at 4 examples of parametric equation problems. So let me share the document camera for you guys. All right, so question, we want to sketch the given parametric equation and convert to a rectangular coordinate equation. And so that's just a fancy word, for an equation with x, y's, and square roots and squares and all that kind of stuff. So get rid of the t. So eliminate equation by eliminating the parameter. So the first one we have is x is equal to 8t minus 5, and y is equal to 4t. And in this one, it tells us that t has to be greater than or equal to 0. So if it doesn't tell us that, then sometimes we can just pick whatever values we want, -2, -1, 0, 1, 2. But in this specific case, it's telling us t has to be strictly greater than or equal to 0. So that means 0, 1, 2, 3. Let's try those points, see what that gets us. So my x is going to be 8t. So 8 times 0 is 0, minus 5 is minus 5. If t is 1, 8 times 1 is 8, minus 5 is 3. If t is 2, 8 times 2 is 16, minus 5 is 11. So I'm going to stop there because we're already getting pretty high in the numbers there. And then how about y? Y is 4 times t. So 4 times 0 is 0. 4 times 1 is 4. 4 times 2 is 8. All right, so we got to graph this thing. So our x is -5, 0. So that's this point here. And then 3, 4. And then 11, 8. So we're not going to continue this thing off to the left because this is as far left as we're going, the -5, because t has to be greater than or equal to 0. So we actually get what? It's kind of hard to tell, but we're getting this sort of curve going this way. And of course, the right side will go on forever because if I put in 3, I'd get 24 minus 5, 19, and then 12. So somewhere, way up here. So the right side will keep going forever, but the left side, that's where it starts, and that's as far left as it goes. So that's the curve I get. And then as for getting rid of the parameter, remember what we want to do is get one of the equations to be t equals something. So if I use the y equation, if y is equal to 4t, well, if I divide both sides by 4, that tells me that t is y over 4. Whoops, let me move that there. Oh, so actually these points are in line, I guess. They're not really a curve, it's a straight line. So now plug that into our x equation. So we get x is equal to 8 times t, which is y over 4, minus 5. So the 8 cancels with 4, gives us 2. So we get x is equal to 2y minus 5. So that's what we get for our equation when we convert it. And again, if I had a actual grid spaced out right, this would just be a straight line, not a curve. So it would be a straight line going through these points. All right, second example. We have x is equal to the square root of t. Y is equal to 9 minus t. So in this case, it doesn't tell us, well, t has to be, between these values or t is greater than this, but we can figure that out on our own, right? Because x is square root of t. If we use our properties of domain, that means that t, even though it doesn't specifically tell us because of the x, t has to be greater than or equal to 0. Again, it doesn't tell us that in the problem, but we can figure that out because I can't have negative square roots. So again, if I build a table, now here, I'm going to be a little bit creative with the numbers that I pick. I could pick 0, 1, 2, 3, etc., but then I get what? Then I'll get like square root of 2 and square root of 3, which aren't nice numbers. So instead, I'm going to pick 0 and 1, because I can do square root of 1. And then I'm going to do what? 4, because that's square root of 4. I can do that. And then I'm going to do 9. So I'm picking all the perfect squares, right? So when I plug in t into x, square root of 0 is 0. Square root of 1 is 1. Square root of 4, 2. Square root of 9, 3. And again, you could do 0, 1, 2, 3. You're just not going to get nice numbers. You're going to get square root of 2, square root of 3, etc. Now, plug in our values for y. 9 minus 0 is 9. 9 minus 1 is 8. 9 minus 4 is 5. 9 minus 9 is 0. So we have one point at 0, 9. So up here, 1, 8, 2, 5, 2, 5, and 3, 0. Again, we're not going any more to the left because we got this point here at the left by the limit of our domain. And so this is what? This one actually is like the right side of a parabola, right? Pointing downward. This side, we put the arrow at the bottom because this would keep going. I could still do 16 and 25 and whatever and get more values here. But now for converting which way we want to go. So we have x equals square root of t. So I can just square both of these sides and I get what? X squared is equal to t. Sorry, let me put that there. Now, what we have to be careful with is if this said x equals t squared, instead, I could take the square root, but remember when you take square root, you have to do plus or minus. So sometimes if we have x equals t squared, that's not the best way to convert this because we got to deal with that plus and minus value. So usually convert the other equation. But in this case, because it's just square root of t, I don't have that plus minus issue. I just square both sides and I get x squared is equal to t. Now plug that into my equation here. So t is x squared. I get 9 minus x squared. And if you remember on the content video when we were talking about these, the equation we end up with, and so actually what in this case, 9 minus x squared, but x is greater than or equal to 0. Because 9 minus x squared is what? It's a parabola turned upside down, slid 9 units up. But that would give us the whole parabola. We don't have the whole parabola because of this square root of t. We only have the right side. So we have to put this restriction in that, okay, it's 9 minus x squared, but x is greater than or equal to 0. Because remember, this equation has to give us the same picture back. If it doesn't give us the same picture back, then the equation's not correct. So that's why we got to add this piece here that x is greater than or equal to 0. All right, now I'm going to switch it up a little bit. In this case, we have x is equal to 4 cosine of t, y is equal to 5 sine of t. So now I don't want to pick -2, -1, 0, 1, 2, because those are going to make a big mess for me, right? So again, I need to be creative with the values I pick for t. And so I'm going to pick 0, and I'm going to pick t is pi over 2, and t is pi, and t is 3 pi over 2, and t is 2 pi. So it's what? It's all the values on my unit circle that are on the x and y axis. And why do I pick these? Well, because on the x and y axis, sine and cosine are either going to be 0, 1, or -1. And then it makes my math nice and easy. So if I do x first, so cosine of 0, that's 1 times 4 is 4. Plug in pi over 2. Cosine of pi over 2 is 0. 4 times 0 is 0. Plug in pi. Cosine of pi is -1. 4 times -1 is -4. 3 pi over 2. Cosine of 3 pi over 2 is 0 times 4 is 0. And now we're back around the circle, so I should end up with the same value as here. Cosine of 2 pi is 1 times 4 is 4. So again, you can see why we pick those values, because they're either 0, 1, -1, and it makes our math really easy. Now let's do y. Sine of 0. Sine of 0 radians is 0 times 5 is 0. Sine of pi over 2 is 1 times 5 is 5. Sine of pi is 0 times 5 is 0. Sine of 3 pi over 2, -1 times 5 is -5, and then 0 again. So our first point is 4, 0. Our next point is 0, 5. Our next point is -4, 0, 0, -5, and then back to 4, 0. So I know from these points, it's like, oh, it must be a diamond if I connect the points. Well, it's not. Because if I picked all these points in between, like pi over 6, pi over 4, 3 pi over 2, what I'm going to get is a figure called an ellipse. So it's this nice smooth curve going around this way with the ellipse. And in what lesson is it? Lesson 18, we talk about conics. We'll learn about ellipse at that point. But that's what we get. We get an ellipse going 4 units left or right, 5 units up or down. So the sketching of these isn't normally that big of a deal. You guys are pretty good with this. The problem now comes with the conversion. Because before we were doing what? We were solving one of the equations for t and then substituting it into the other one. But if I did that now, if I have x equals 4 cosine of t, and I'm like, oh, divide everything by 4, and then take cosine inverse. So I have cosine inverse of x over 4. Now plug that into y. I have what? I have a huge mess. I don't have just x's and y's and numbers. I have a bunch of trig functions and inverse trig functions. So that is not how we do these. Instead, what we're going to do is use formulas that we've encountered throughout the semester. Specifically, I guess I would ask you, all right, if you had to do this on your own, are you stuck? And the answer might be, yeah, I'm stuck. And that's a good thing. Why? Because when we're stuck, we use what? Where we try what? We try the Holy Grail. Well, what is the Holy Grail? The Holy Grail is sine squared t plus cosine squared t is 1. Okay, well, do I have sine squared? No, I don't. But I have what? I have y is equal to 5 sine of t. So how do I get sine squared out of this? Well, I divide both sides by 5, and then I square both sides. So I get what? Y squared over 25 is equal to sine squared of t. So if sine squared of t is y squared over 25, that's all I'm going to replace right here. Y squared over 25. Because by my conversion, sine squared is y squared over 25. So just replace it in the Holy Grail equation with that. And same thing for cosine. So I had what? X is equal to 4 cosine of t. So divide everything. Whoops, not x squared. X is equal to that. Divide everything by 4. Square both sides. I get x squared over 16 is cosine squared t. So plug that in over here. So x squared over 16 is 1. Now, do I have x's and y's in numbers? Yes, I do. So this equation has now been converted into a rectangular equation. And again, in lesson 18, we will see that this equation is an equation of an ellipse with 4 units left or right, 5 units up or down. So these are a little different. We're not going to solve for t. We're going to use our trig equations that we've had throughout the semester, and then plug in what we can convert from our given parametric equations. All right, last but not least, we have x equals sine of t and y equals cosine of 2t. So first of all, before we even get going, when I see this 2, this should be screaming at me what? Double angle. So probably at some point in this problem, I'm going to have to deal with the double angle formula. But for now, to sketch it, because it's trig functions, I'm going to use the same values, 0, pi over 2, pi, 3 pi over 2, 2 pi. And so x is sine of t. So sine of 0, 0. Sine of pi over 2, 1. Sine of pi, 0. Sine of 3 pi over 2, negative 1. Sine of 2 pi, 0. Now, for my y value, it's cosine of 2 times t. So whatever my value of t is, I have to multiply it by 2, then take cosine of that value. So when I plug in 0, 2 times 0 is 0. Cosine of 0 is 1. When I plug in pi over 2, 2 times pi over 2, well, the 2's cancel out, so I just get pi. Cosine of pi is negative 1. Plug in pi. 2 times pi. Cosine of 2 pi is 1. 3 pi over 2. Well, again, the 2's cancel out, so I'm left with 3 pi. Cosine of 3 pi is negative 1. And then lastly, 2 pi. 2 times 2 pi is 4 pi. Cosine of 4 pi, that's the right side of the unit circle, so that's positive 1. So this is going to give us an interesting graph. So we have to be careful with what's happening here. Our first point is 0, 1. So up here. Our next point is 1, negative 1. Our next point, 0, 1 again here. Our next point, negative 1 here. And then lastly, 0, 1. So this graph is doing what? It's going here, and then bouncing back up to here, down to here, and then bouncing back to here, and bouncing back to here. So this is it. This is our only graph, right? We don't put the lines down here with arrows like, oh, this is an upside down parabola. No, it's not. It's an upside down parabola, but it stops right there because this thing just keeps bouncing back and forth and back and forth. So we need our equation to basically be an upside down parabola, but then we'll have to put in restrictions like, okay, x is either between negative 1 and 1, or y is between negative 1 and 1, something like that. So now our conversion. Again, because these are trig equations, I'm going to use my trig equations and not just solve for t. And so I'm going to use what? It kind of told us here at the start, double angle. So I'm going to use one of my double angle formulas. And I have 3 of them, right? So which one do I want to choose? Well, my other parametric equation has sine in it. So I'm going to choose, so I have y equals 2 cosine of t, but we know what? 2 cosine of t, excuse me. We have cosine of 2t. One of my equations is 1 minus 2 sine squared of t. So I'm plugging this in to this equation. So instead of saying y is equal to cosine of 2t, I'm going to say y is equal to 1 minus 2 sine squared of t. Now, do I have sine squared? Not yet, but if I square both sides of this parametric equation, we do it in red so we know that it's not what we started with. If I square the right and I square the left, I get sine squared is equal to x squared. So therefore I have y equals 1 minus 2 x squared. But again, this will give me what? A parabola multiplied by 2, flipped upside down, moved 1 unit up by our transformations, right? But I don't want that whole parabola. I want only the parabola where x is between negative 1 and 1. So this would be your final answer. If this was on a test, this is what you would have to put. Because if you just told me the equation, that gives me the whole parabola. And I don't have the whole parabola. I just have that top of the curve. So that is it. That is our example video for parametric equations. Should be enough to get you guys through the various problems you have. So come on back and we'll look at our last lesson of the semester, lesson 17.